All right, so we're going to pick up right where we left off last time. We were looking at how to write generic code in C in order to not have to write a function, basically a search function for integers, a search function for doubles, a search function for books. And we did that by using comparators. A comparator is something that takes two generic void pointers, and then what you do is you force them to become the types that you're looking for in books or doubles or integers, right? Then you perform whatever standard you want to compare those two elements by. Remember that you return something negative, positive, or zero depending on the relative ordering of them. So if you wanted to reverse this ordering, of course, you could go ahead and reverse these less than, greater than symbols. Or you could have a comparator call another comparator, which is what we'll do when we eventually get to it. All right? So what I wanted to do is I wanted to take another look at this search array function that we made. Remember that it takes a generic void pointer array, the number of elements in the array, and the number of bytes in each element. Why? Because we have to do this pointer arithmetic ourselves. Right? If it were integers, it would know that every integer is 4 bytes. So the first one is here, the next one is 4 bytes next, 4 bytes next, 4 bytes next. If it's a double, then it's 8 bytes, 8 bytes, 8 bytes. But if it's a book, then it needs to be told that, right? And so we need to be told the number of bytes in each element. And if that matches the key, then our comparator returns 0, and we return the index at which we found it. So now that we have this and we understand how it works, we're going to throw it away. Because we don't generally want to rewrite these things if they are provided by the standard library. In this particular case, there is a function called lfind. There's also one called lsearch. The L there stands for linear, and we'll talk about that later when we compare these things. And it looks almost exactly like what we designed. It takes a key, so we put that last, but that comes first. It is a const void pointer, right, because it is generic. We're not going to be making changes to it. Base ends up being our array, right? The number of elements in the array, the number of bytes each element takes, and then finally the comparator that you want to use to compare the two elements. So now that I've removed that function, let's go ahead and modify our code here to use the built-in function. Before we do that, though, let's take a look at the return value here. Is it the index at which it found it? Nope. It's a pointer, a generic pointer. It returns, it walks linearly through an array, comparing each element with one to be sought by means of a supplied comparison function. Wow, they're getting really fancy with their wording there. Blah, blah, blah. If no matching element is found in the array, it copies the key. Okay, so no, ignore that. Where should we look here? Return values, there we go. Both return a pointer to the first element that's found, or that matches the comparator. If no element is found, well, what does it return? lfind at least. It returns null. So let's come over here and modify and get rid of our index of here, okay? So what I want is a pointer, right? So this will be, I'm searching an array of integers, so I want an integer pointer. And I'll call it found, int. And I will be making a call to lfind, okay, instead of index found. Now, what are the arguments again? Let's take a look. First of all, we provide the key, a pointer to the key. In this case, the key is called key, and I need to change that into a pointer, so ampersand. The next argument is the array that you want to pass in, then the number of elements, and then the width. So number of elements here is going to be n. The width, the number of bytes each one takes. How did we do that? Size of int. Right? So number of elements, sorry, I forgot the actual array. AR, there we go. The array, the number of elements in the array, the size of each element, the number of bytes of each element. And then finally, the comparator that you want to use. So compare int. There we go. Now remember, it returns a pointer if it's successful. So if found int is not equal to null, then we know that we found what we were looking for. That's when we print this out. Right? So I found %d at It's no longer an index here, but it's going to be at memory address %p. So we will take the, key, the found integer here, and we will dereference it, which is safe because we know that it's not null. And then we'll go ahead and print out the actual memory address. What's the alternative? What if we don't find it? Printf %d not found, right? End the line. And here it will be my key. Okay? Now do be careful. Let me go ahead and get rid of the rest of this stuff for just 1 second so that it compiles. Yeah, GCC. I'm in demo here. There we go. .c. All right, there we go. Oh, sorry, implicit declaration. Where is it located? There's a search library. So let's go ahead and include that up there. All right. Some of the others are built in and you don't need to include the search library, but there we go. So this is a mistake I made yesterday, and it sent me down a rabbit hole trying to figure out why it was done this way. Let's go back over here and let's ask a question. So yeah, this is going to be the array, right? It's going to be const void star, right? It's a pointer, and you're not making any changes to it. The number of elements in the array. Have we ever designed a function that passed the number of elements in an array where you were not going to be making changes to that array as a pointer? No. So I was baffled by this too. Why in the world would they have done this? I even looked at the source code of a couple of different systems, including BSD and whatever the Mac source code is, and they don't use it. They never write to this, right? They never actually change this value. So the big question is, why isn't it const? Why is it even passed by reference when it could be, it's going to be read only? You're not going to be making changes to it. I have no idea, right? And I could not find a satisfactory answer. I couldn't even find anybody asking this question online. And my only guess is because it needs to match L search, right? Or you're going for the same signature here. And L search does make changes to the array. What it does is it goes through and tries to find it. And if it doesn't find it, it appends it to the end of the array. Crossing your fingers that there's enough room to put it there, right? Because it doesn't allocate more memory for you. Okay? So why is it done like this? I have zero idea, but we need to conform to it. And what I mean by that is we cannot pass in n like this. What we need to do is we need to create a pointer, which is of type size t, and I'll call it size of All right, there we go, is equal to, oops, sorry, I need to do it like this, and then I'll set that equal to n, n. And then I can pass in size of There we go. Yeah, it is really kind of silly. Comment online there. I have no idea. Right? I think it's a design flaw, right? But whatever. In fact, if you look at, I don't know, let's look at the full description here. See also history, functions appeared, no. All right, so this is on Mac OS, but I was looking at the documentation for for something else. Maybe Ubuntu or something like that, and they had a history here. The naming is unfortunate. In other words, why did you name it lfind and lsearch? Right? It is unfortunate. It doesn't really describe what it does. Search tells me that it's going to search it. Find it tells me that it might be find it and then put something in there. Right? Find and replace is basically what it's what lsearch is doing, but they're backwards. Not only that, but why are you putting L in front of it? Well, it's linear search, and there's a different B search, binary search. But it's just somebody's commentary on the bad naming there. So people are not immune to, I mean, even top programmers are not immune to design flaws like that. Right? So let's go ahead and run this. Oh, by the way, what am I searching for? I'm searching for 8. Do I actually find it? Yes. I found it at that blah, blah, blah memory address. Yeah.
What's the
Size underscore t. That is a built-in type. It is usually an unsigned integer. Let's find out. Size type. All right. Type t. Need type t. Okay, we're going to go down the rabbit hole here. You can, for all intents and purposes, you can treat it like an integer. It's just a number, but it's used specifically for number of bytes. And what it actually is going to be system dependent. Yeah, I don't know what the actual definition would be because it ain't there. Oh well. It is used all over the place. Instead of, you know, number of elements, it's size t. It's not an integer. It's not an integer. But normally you could pass in an integer and be fine with it, but not in this case because it is passed by reference for some reason. Do not ask me why. I tried to find out. All right, so let's go ahead and do this for Burr, right? How do we do it for Burr? Well, how do we change it? Well, first of all, I need size of Burr, right? And it's also 8 elements, excuse me. And instead of finding the integer, I'll find double, right? Find double, found it at double, double, right? And compare double. What else changes? Well, my key for the double array here is key D. Otherwise, it's Burr, and it's size of Burr, and it's size of double. Right? But I didn't have to rewrite the algorithm. I didn't have to rewrite the find function. It was already built into the language. All I have to do is define this comparator for it. Right? And where were we searching for? 8.5, GCC. There we go. And we found, 0. I'm searching for 0. Oh, sorry. Percent %F and percent %F and key D. There we go. Oh, what's found double? Oh, sorry. No, this is right. Found double. Oh, duh. What else do I need to change? That one right there. All right. Found 8.5 at that memory location instead. Let's go back and search for something that doesn't exist. Say 42 and 8.4. Is that not in there? Good. GCC and run it again, and we'll see that they were both not found because lfind returns null. Okay. Finally, what do we do about books? I've got a bunch of books here, 4 books. Let's go ahead and try to search for a particular book going through this pattern here. First of all, I need a key, book key. Right? Okay, how do we want to search? Well, the only comparator that I wrote here was by title. So let's search for the title Harold. Okay. How do I do that? I'm not going to be able to pass in a string because if I've got an array of books, the key has to be the same type. You have to compare apples to apples, oranges to oranges, books to books. So I need an actual full book here, right? So I could call init, right? I could declare it and then call init book, right? Book key, and then pass in everything Harold, right? And then Stephen Wright, or the rest of it, right? If I had the rest of this data though, what's the point of searching it for it, right? You've already got your copy of your needle. Why go in a haystack to find another needle, right? So what we typically do instead is we make this into a dummy key where we don't worry about the initialization of the other things like the first name, the last name, et cetera, et cetera. So what I'm going to do is I'm going to create a dummy empty book, but with the title defined. Now to do that, I need to remind myself what the order was. Okay, the order here was title, author, published date, and then rating. So let's come back over here. I think I can do this, I hope. Title, author, published date, rating. So title should be Harold. Author is going to be another structure here, which has a first name and last name. But I don't care about those, so I can put in those dummy values, or I could put in, even better yet, null and null. First name missing, last name missing. That was what author was, right? First name, last name, right? Not demo here, right? Then we had the date. Oh, darn it. I don't have a good memory there. Yep, the published date, which is 3 integers. So that can't be null because it is an actual structure. So I'll just go ahead and put in zeros for everything. Default values. You did this in your lab last week when you wanted to create an empty RSS feed with default values. Right? Here's another way. The last one is a rating, so we'll just go ahead and say 0.0. Right? So GCC. Oh, okay, fine. Init book. All right, and then let's go ahead and GCC compile book.c. Wonderful. Now GCC book.o and demo.c. There we go. So that creates this book key right here with the only value that's specified being the title. Okay. Now let's go ahead and find the rest of this stuff. Cut, paste this. And how is it different? Well, it's no longer the size of BR, it's the size of books. Right? And it's not N, it's 4, because I didn't want to make 8 books here. Okay. Found book. Got to be careful. Is it going to return a double? If it finds it, it's going to return a pointer to a book. My key here is the book key. It's not BR, it's books. Size of books, right? Then size of a single book, and then compare, what did I call it, by title? Compare book by title. Right. Now I found %F, nope, found the book at memory location, whatever. Right. I'm not going to print it out because that would involve calling a function to do so. Found book, there we go. Not found. I'll leave it like that. Of course, you could go back to your toString function, call that, and then print it out. So let's go ahead and run this. GCC, there we go, a.out. Oh, not found, why not? Herald, Herald. Book, book, size of books, books, book. Compare title. Title, title. Say what? Thank you. Copy, paste, copy, paste, copy, paste. Right? Bad habits to get into because, there we go, found the book at memory location, whatever, whatever, whatever. If we were searching for something else, like only you can save humanity, right? Now, that book is not in my collection, so we'll end up with a not found there. Okay. You could also search by author. You could search by date. You could search by whatever, just using lfind. Let's do all that again over here in Java. Right? So first of all, I've got, and I'm not even going to bother writing my own find. We're going to immediately jump to the end because it's built into the language. But what we do need is a comparator for integers in this case, and then a comparator for books. So let's do a comparator for integers first. Rather than a function, because in Java, remember Java is an object-oriented programming language, everything belongs to a class or is a class. We can't just have these functions that exist out there. Here's a function. In C, a function is what we call a first-class citizen, meaning that it's built into the language. Integers, doubles, functions, those are first-class citizens, and because we can directly access them. In Java, that's not true. Right? In Java, everything has to be part of a class. A class is the first-class citizen. Right? So a comparator, right? Who would have thought that you would call it comparator? Comparator, I spelled it correctly. We also parameterize this. What is this a comparator for? It's a comparator for integers. Right? And I will call it, like I did the other one, compare int. Right? Now, I can leave it at that. But did I define what this comparator is or what this comparator does? No. In fact, what is this value right now? Like any other variable, it's just null. So here's some new syntax. New comparator for integers. And then I immediately put in curly brackets here. What this is called is an anonymous inline declaration. So remember, everything is a class or belongs to a class. This is technically still a class. What I could do is I could take the functionality that I'm about to write and I could put it into a completely separate source file over here, like a new class, my awesome integer comparator, right? But what use is it? It's a one-time use thing, right? Whereas with books, you can create that book, that book, that book, 50 different books, right? That makes sense. Why do you need 50 different copies of your awesome integer comparator? They all do the same thing, right? So we don't generally do that. Instead, we do what's called an anonymous inline declaration here. We are going to declare it and put it all into a variable and not into a separate source file because we don't need it. The only thing that it implements, and this is called an interface, we'll talk about that in CS2, don't worry about it. The only thing that it implements is this public int compare function. What is the integer? It returns something negative, positive, or 0, depending on the relative ordering of those two integers. It takes integer, and the auto-generated code here calls them O1 and O2. I'm going to call them A and B. Right? But the fact that they are integers is what it's looking for, because this is a comparator for integers. If I try to make it as a comparator for integers, but then I took a double, right, that ain't going to compile. They have to match. Apples to apples, oranges to oranges. Undo, undo, undo. There we go. Now, all I need to do is to define the behavior in here, right? So if A is less than B, then return something negative. Else, if A is greater than B, then return something positive. Else, return 0. Exact same pattern as C. This entire pattern is universal in almost every programming language that I've ever seen. This comparator pattern. Okay? Once we've got that, we can now use it. There's a collections dot find, nope, dot search, nope, contains, dot index of. There we go. Index, no, not of sublist. What is it? Oh, you know what? Maybe it's in the actual list itself. So numbers dot find, what is it? Get iterator. Isn't it index of? Yeah. Yeah, there we go. There, index of. There's no comparator though. Darn it. Java linear search list dot index of, no, dot find, no, dot, no. I've been maybe I've been lied to. There, collections dot. All right. There's binary search. There's copy, empty, empty, empty. Fill, last index of sublist. Min, max. Swap, sort, synchronize, blah, blah, blah. Oh, really? There's no index of. Using a comparator. That kind of kills all, doesn't it? All right, so Java, linear search method, comparator. It should take a comparator. We really don't have this linear search in Java. Okay, thanks. That's not helpful. There was a question that was answered, right? That's the same one. Search an array list using a comparator. Yeah. All right, the answer should be, that's for a map. I want an array list.
Wouldn't you do like compare in that?
I mean, you could. So if you did this, if you just did this list dot index of, right? That's what that is doing is that's assuming that it's naturally comparable, and it is in this case. Come on, index of, or not list, but my numbers. There we go. All right. And what that's doing is that's using the internal dot equals, and so it will work in this case, but that's because integer is built in, right? What I need is to make this into a configurable version of this by passing in the comparator, compare int. That's what I need. Right? So, all right, if it's not built in, screw it. We'll go ahead and write our own. Right? All right, so let's write it. Public, static. Actually, no, that gets into parameterization, and I don't want to do that yet. Sorry. Really, array list. You say a map, array list, dog. There's compare by name, toString. No, there's not. Fine. I'll show you a different one. I wouldn't have put in a linear search, no. At least a built-in one. Darn it, really? Fine, preview. Collections.sort numbers by compare int, right? And then what I can do is I can do B search, collections.B search, binary search. There we go. Numbers and compare, compare int. There we go. And that will return an int index of, there. What are you complaining about? List. Oh, yes, you do exist. Dot binary search. Oh, I need the key. There we go. Binary search, numbers, the key is key, and then finally compare int. There we go. All right, and then let's print it out. System.out.printf, let's say, found %d at index %d and the line, and we're searching for the key and index of. There we go. Now let's run this. 8 at index 6, excuse me. So we're searching for 8. It's found it at 0, 1, 2, 3, 4, 5, 6. We got lucky there. What was I actually doing? I was sorting it so that I could use this different type of search. A binary search is something that is far more efficient, in fact, orders of magnitude more efficient, exponentially more efficient, but it requires it to be sorted, right? So this is where we were going after the break here, right? But if without a linear search here that doesn't require it to be sorted, I can't do it. If anybody's looking, like what's a linear search in Java right now, they can look it up for me. But in any case, we will eventually get to sorting because we do searching first and then sorting, right? But it has actually changed my array here. Let me show you. System.out.println numbers, or my list, I should say. Whereas before it was unordered, 7, 1, 8, 6, 2, ... right? It is now sorted. Why? So that it can exploit that sorting structure in order to do more efficient comparisons. Right? The way that it works, here's a preview, is if you're looking for 8, what you do is you jump into the middle. Do you even need to bother with this lower half after seeing, oh, here's 5? If 8 is in the array, or 8 is in the list, where would it be? Over on this side. Right? So by making one comparison, you can basically cut it in half. Then, once you've got this half, what you do is you jump into the middle. Right? In this case, 8, say. And you find it immediately with only 2 comparisons. Whereas up here, if you were searching, say, for 3, what would you have to do? You'd have to go all the way to the end. Right? Making 8 comparisons. All right, let's do the same thing for books here. I've loaded up the books here. I put that in the function, and I'm loading them up from that CSV file. The first thing I need to do is create a dummy key, right? So in that case, it's going to be a book key, right, is equal to a new book. Remember that we wrote several different constructors here. Actually, no, we wrote several different constructors for another one. I only have one constructor here. So if you want to create a dummy value, dummy value here, what would you do? You'd pass in, like, I don't know, what do I have in there? Dune. And then null for the author. And then what else was there? There's an author, there's a local, the published date, and then a rating. So default values, null, null, and then say 0.0. So that it searches by the title. Okay, and then you would have to sort it, binary search it, and then print it out. We won't print out the numbers here, but index of, I'll just reuse that variable there. Instead of numbers, we're going to be searching books. Instead of that key, we search the book key. And instead of this compare int, we need a compare book. We'll write that in a second. Otherwise, you found the book, %s, book key, books.get index of, and then at index of. There we go. So the last component here is to build this thing. What would it look like? It's also going to be a comparator, right? But is it a comparator for integers anymore? Nope. It's a comparator for books. Call it compare book. By title, if you want to be even more descriptive. So I'll need to change it down there. There we go. Oh, and then sort the books. Right, there we go. All right, so I followed the exact same syntax as up here. Anonymous inline declaration like this, new comparator. And by the way, why is it called anonymous? Well, if I went over here and I created an actual class, I would have to give it a name, right? My awesome book comparator, whatever. That has a name, it's not anonymous. What's the name of this class? There is no class, so there is no name, right? So it's an anonymous inline declaration, okay? I'm going to let it auto-generate that compare book, A and B. And now in here is where I do the business logic of comparing those two books. All I want to do is compare the title. So A.title, A.getTitle, and I want to compare that to B.getTitle. That compare to method is built in. This is a string and this is a string. You can compare strings, and guess what? It returns something negative, positive, or 0 depending on the relative ordering of those things. So just return this. That's it. Save it. Should compile, and let's run it. I was searching for Dune. There we go. Found Dune, Frank Herbert at index 5. What else was in there? I don't know. Dune, Valerian Jihad. Right. That's not in there. I'm pretty sure that that's not in there, but let's find it. Nope. Index out of bounds exception. -2. Oh, it's returning a flag value there, a negative value to indicate that it did not find it. I need to write code to check for that. Okay. Let's restore this back to Dune. Now that's how you write comparators. Modern Java, it's even easier. Let me replace this entire thing. All right. Actually, let's do another comparator so I don't get rid of it. Comparator for book. I don't know. By author, then date. Right? So what I want to do is I want to compare it by the author. If they have the same last name, say Herbert and Herbert, Brian and Frank, right? Two different people, but the same last names. I need to find Frank in particular. So I need to compare by their last names. If they have the same last names, then I need to go to the first names. If they have the same first names, then maybe I want to look at the date that the book was published. That sounds like a lot of work, right? I mean, it's going to be getting this for the author's last name, and then the author's first name to break that tie, and then we need to get the date, the year, the month, the day, right? That sounds like 6 lines of code to me. But modern Java provides a much more streamlined way of doing this, right? Is equal to comparator dot comparing. Right? What do you want to compare? I want to compare the book author. Right? Dot then comparing. Or sorry, it's author, isn't it? There we go, author. Then comparing book date. What is it? Published date. All right, so it's author and then publish date. Publish date. There we go. Book, come on, what's wrong? Okay, I know what's wrong. We'll fix it in a second here. Let's go. Let's do something simpler then. Let's reproduce the title instead. Undo that. Let's keep that for a second, and then let's do something else. Let's go by title, then date. There we go. Title. It's not going to have a problem with title because it's a string. It's built in. It knows how to compare them. Comparing. Come on, it should work here. Comparing, then book, date. This is right. This is correct. Comparing. No, did I just misspell it? My notes are right. Got comparing. Book. Oh, I know. Duh. Sorry. It's not title. It's what? Get title. And then what is this? Get publish date. There we go. All right. So some new syntax addition here. Right. So first of all, this is what's called chaining. Right. What I'm doing is I'm comparing. I'm creating a comparator, comparing first this thing. That returns itself, so that I can go dot then comparing, and I can chain this. Right. I can say then dot then comparing. Right. Then comparing. Then comparing. Right. It's a way that you can break ties really, really easily without having to write a bunch of if code, right? You can chain these things together. You can chain them as many times as you want. Then compare, and you can also handle nulls, right? Dot nulls, what is it, nulls first? Or they're reversed, right? So instead of writing a brand new comparator that you have to then reverse the values, you can just go ahead and go dot reversed. Right? And that's dot reversed on all of them. Dot nulls first, isn't it? Isn't it nulls first? Anyway, I don't know where it is. But anyway, this should work. It's going to compare the title, and then it's going to compare the published date. Let me show you how it works, or in action here. Let's go ahead and sort them. So collections.sort books using this. By title, then by date. It's not going to be that useful, but whatever. Then for book in the collection books, system.out.println B. There we go. All right. There it is. Is it in order by title? A to Z, right? Or A to W in this case. It's not going to be smart enough to figure out that articles don't count when you're sorting something, right? But you can build that logic in if you really want to. But otherwise, we don't have anything that is repeated here. So let's go ahead and make another comparator by author, then by date. Right? Now this isn't going to work because it doesn't know anything about authors. How do you compare authors? Get published date. Right? Oh, before I do that, this is brand new syntax, isn't it? Colon, colon. I think, don't quote me on this, but I think that this is originally from Pascal. It's certainly from C++. What it is it's a function selector operator. So we've got this book class, and it's got functions. How do we refer to that actual function using this more modern syntax here? It's kind of like a function pointer, but it's still not a pointer because in Java you don't have pointers. But it is a way to refer to this particular function or this particular method in that class. So the syntax is going to be the class name and then the function name, and again, no parentheses here. You're not actually calling the function, right? That would be invoking the function and executing the code in that function. You're just referring to the function. Now it's complaining about this because if we go over here to the author class, so there's the author class. It's not what's called naturally ordered. For example, if we were to look at the string class, it's naturally ordered because it is comparable. You can take one string and compare it to another string. That's because they put in the code to do that, compare to. We already used it. There it is. Well, not there, but where is it? Compare to. All right, compare to. No. All right, where it's somewhere in here. We can search for it later. Right? But in any case, we can do the same thing with our own classes. Here's one author and here's another author. I could create a comparator, right? Or I could make this comparable, right? So a comparator is a noun. Comparable is an adjective, right? So implements comparable for author. There we go. And that defines one method called compare to that takes this other author, that author. Right? So we are going to compare, we need to compare this author to that author. And I don't like calling it that, but I want to drive home the fact that there are two authors here. The object itself, just like there were two airplanes, right? When you were comparing the distance, there's this airport. There's this airport, and then the airport that is given as input. That airport. I don't want to call it that in the end, though. How do we compare those two things? Let's compare their last name, because that's really all we have. Author last name and first name. If this were an actual app, I would probably be looking for some sort of unique identifier for every person. If it were a UNL app, that would be NUID. If it were in the United States, Social Security number or tax ID number or something. Right? Here, all we have is a last name, first name. So let's compare their last name first. This dot last name dot compare to that dot last name. Right? Now, if that's non-zero, then we immediately have a distinction, right? Emma by, who was it again? Jane Austen, there we go. Austen and Herbert are two completely different authors. So we could immediately return this if it's not equal to 0. If it is equal to 0, though, then that means that they have the same last names, right? Same last names. So look at the first name, right? In other words, result is equal to this dot author first name dot compare to that dot first name. Right? Now, what if they have the same first name and last name? Then I suppose that we could go ahead and compare them by their birth date. What if they had the same first name, last name, and birth date? Right? Now you need another way to break ties. That's called a total order. It's a mathematical concept in, say, discrete math or something. I'm going to keep it simple. All right, we're not going to be able to distinguish those two different authors. Right? Now over here, get author, it goes away. Why? Because now it's naturally comparable. You already specified how authors are ordered. So we want to compare them by author, by getting the author, but the code to do that has to be somewhere. And in this case, it's right there. So now let's use this one by author, then by date in our sorting instead. And let's run that, and let's look. So now take a look at the titles. Are they in order anymore? Nope. But what about the authors? Jean Arl, Gibson, Heinlein, Herbert, ... I don't have any repetitions here. So I don't have any Brian Herbert stuff. But if it were Brian Herbert, where would he be? Right before all Frank's books. Right? But now look at these. Oh, darn it. I never printed out the actual year, did I? Probably because I'm not loading it, but whatever. Am I? No. This is the correct order. All right. Has anybody read the Dune series? All right. So it's definitely Dune, Dune Messiah, where Paul is killed. Then Children of Dune, where they take over. God Emperor of Dune, Herod. Yeah, this is right. This is the correct order. In published date order. Right? We can open it up really quick and look and see the actual data. Right. Collapse this. Open this data in Eclipse. And Dune, where is it? Dune, 1965, then 69, 76, 81, 84, 85. Right. That's the order that they were in the file, but that's just because how I wrote it, right? If we wanted to, we could go ahead and mix these up a little bit and I'll show you that it will still work because it actually sorts them properly. So it's still going to be Dune, Dune Messiah, Children of Dune, etc. Question?
Could you explain how the date is being sorted? Like, is it the ordering of the date?
Good question. So I didn't specify that, did I? All right. So let's go ahead and take a look at published date. Well, what is published date? It's the local date. Right? Let's take a look at that class. Guess what they already did for us? It's somewhere in there. Temporal, maybe. Extends temporal accessor. Somewhere in here, they did it for us. Find to, compare to. All right, chronolocal date did it. And they have a compare to method in there, and that's the one that, or no, there's a compare to method right here. There it is, right? Otherwise, it passes that off to another function. That function compares, compare that, and there we go. Now we're finally down to brass tacks where we're actually looking at numbers, right? So if x is less than 0, then what do we return? Something negative. Otherwise, if they're equal, return 0. Otherwise, we return 1. And they're just doing a little fancy ternary operator here. So it was way under the hood. All right, it was, all the built-in types, all the standard types, they're going to have some compare to method built in for you. Strings are going to be lexicographic. Numbers are going to be in ascending order. Right? Booleans are also going to be orderable. I think true comes before, false comes before true. False, then true. Why? Because 0 and then 1. That's the idea, at least. So that takes us all the way up to the need to do sorting, right? I screwed up. I didn't even know that there wasn't a linear function, a linear search function built in. I thought that there was, or a comparator-based one, I should say. There is one that's built in, but not a comparator-based one. So why do sorting? Because you can go way faster. Right? So imagine just really quickly here, let's look at Wolfram Alpha. Right? What if I had not just 4 books or 50 books or something like that? What if I had 10 million books in my database? If we were just to use linear search and they're all just stored in this big giant array or something, what would you need to do? You'd need to start at the beginning and ask, is that the one I'm looking for? Nope, 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 nope. Until you get all the way down to the end. In which case, how many comparisons have you made? That was 10 million, by the way. You've made 10 million comparisons to not find the thing that you were looking for. Or maybe you do find the thing that you're looking for, it's just that it's in the last place, right? And you get unlucky. 10 million comparisons versus I can get it down to this many. 10, 1, 2, 3, 1, 2, 3. I could get it down to 24 comparisons. How? By that divide and conquer strategy that we covered when we looked at recursion, right? Divide and conquer. I don't know how to do all this, but I'll look in the middle. If it's sorted, right, then I can look in the middle and I can say the thing that I'm looking for is either over here or it's over here because it's sorted. That means that I can take half of this stuff and throw it away. In other words, I can go from 10 million down to 5 million, right, with one comparison. I can cut that down further to 2.5 million with one comparison. Only 2 comparisons so far, right? I can cut that back down to 125, there we go, 2 million with 3 comparisons. And you see how you can really, really speed things up. 10 million comparisons versus only 24 comparisons, right? That's an order of magnitude, that's exponentially faster. It's not even an order of magnitude, it's exponentially faster. Right? You are not going to beat that. But the problem is, it's got to be sorted first. So how do we do that, and how do we exploit that structure? We'll start covering that when we get back. Remember, no class on Friday because of a committee meeting. You do have your hack tomorrow. It is due after the break. I would say try to get it done before the break, though, so that you clear out all your stuff off. Remember that the PDC modules and the survey are due on Friday as well. In fact, I'll point out to you that this divide and conquer strategy that we've been kind of teetering around, that's implicit in all the PDC content, right? If you use one processor to do 10 million things, that takes, say, 5 minutes. But if you can take 10 million things and divide it in half and run it on 2 processors in parallel, well, now how long does it take? 2.5 minutes, right? Roughly. Now, what if you ran it on 4 processors, 8 processors, 16 processors, right? And so that parallel and distributed computing concepts, that's what those modules are designed to go to give you. They're codeless. You don't need to write any code. You just need to observe the results, right? That's due on Friday. Any questions? No? All right. Then have a good break.